So let me just make a recall that after Danielle's talk, we'll have the photo of the conference, okay? So it's my pleasure to present the first talk of the day, Daniele Panazzolo from Université de Haute Alsace. And he's going to talk about Bruno ideal and the variety of centers for singular germs of vector fields.
Hello, can you hear me? Yes, I'm very honored to be here. And I'd like to say that I spent a year at Rennes, 2006. And it was very, very nice, very honored to be there. And I mean, the people there are very, very nice, and I think that I felt at home very quickly. So there was very nice interactions with Frank, with Guy Casale, and Jean-Marie Lyon. And I think that is a very nice, let's say, way to receive people and make them feel at home very, very quickly, either from the personal point of view and from the scientific point of view. And that's what I found in Rennes. I think most of people that went there, all of people that went there felt the same way. So I'm going to talk about a result which has already, let's say, the enunciate of the result is due to Bruno. But I call this a very mysterious result because I was not able to find a proof. So I feel it is very, very nice. And I started to work with Maria. So this is a joint work of Maria Martin Vega from Valladolid to find a proof. And I'd like to explain to you this proof. And I hope that it can also motivate some extensions that we're thinking about right now. Okay. So what's the subject? We start with, I denote by this, a germ of singular vector field. Okay, so in the neighborhood of the origin Cn. And we'd like to understand how the leaves of the foliation behave in the neighborhood of, let's say, in a sufficient small neighborhood of the origin. And of course, there is this notion that Andrea Bellotto talked about, this, what we call an elementary singularity. But I think that this is quite a little bit misleading because what we mean by elementary singularity is something that we cannot improve by further blowing ups, roughly speaking. But we are very far from understanding what happens when you are in a neighborhood of an elementary singularity, most especially in the case where the dimension is high, right? So there's a lot of works about elementary singularities in dimension 2. But starting from dimension 3, it's a very, very wild world. And I don't think that we are very far from understanding what happens. So, OK, so the best method to try to understand this is to use some kind of normal form theory, right? So I would like to explain to you, let's say, an approach to the normal form theory for this kind of object, a la Martinet, because I think it's the best way to. I like very much the way that Jean Martinet explains this in a Bourbaki seminar, because it's completely, let's say, intrinsic and relates, roughly speaking, transforms this problem into a linear algebra problem in a, let's say, in a projective system. Okay. So the question is to find normal forms, right? So I just fix some notation for me. This is the ring of a convergence series with a maximal ideal M. So we can look, it's very convenient to look at the vector field like this as a derivation on O, which is what we call a local derivation, in the sense that let's say, it satisfies, of course, the Leibniz rule. Okay. But it also maps the maximal idea into itself. Okay. So if you have these two properties, you can easily prove that, of course, it maps all powers of the maximal ideal into itself for all k, because of these two properties. And then you can look, in fact, in the action in the jet space, which is the quotient of this m by nk. And then you have the derivation, which, let's say, it restricts your derivation on this jet space. Let's call it like the k. So, of course, this is a finite dimensional vector space. And let's say, yes. So the idea is that you have, let's say you have this set gk with the projections. This is the projective system. Where pk, of course, is a KL is just a projection map, which takes, let's say, some polynomial, some gk jet, and then maps it to a gl jet. And of course, everything is compatible with these induced derivations. And OK, so now there is another objective that is interesting, is the completion, is the projective limit of this gk as k goes to infinity. And this, of course, it's the same thing as saying that you have the ring of formal series, right? In x1x here. So I have no concern about the convergence here. And some objects will be much easier to define here because of this property of passing to the limit. So of course, we are going to talk in this, we're going to say in this talk that there are two types of derivation. There is a derivation. Let's write it in this way. So this is the coefficient. So this is a formal derivation if the coefficients lie in O tilde, and this is analytic derivation if fi lies in O, right? But of course, you can think as an analytic derivation can also be extended as a derivation on this formal ring here. So what's, let's say, Martinet approach to the normal form? Martinet. To normal forms is to say that choosing a normal form is the same thing as considering the Jordan decomposition of a derivation. Okay, so what you do is that you take any derivation, but now as seen as a derivation in the formal ring O tilde, and then there exists a unique decomposition of delta in two terms. Okay, so this is the same simple part. And this is the nilpotent part. And in fact, to obtain this decomposition, let's say it's what you do is that you just work on these finite dimensional vector spaces, and then you just see this, let's say, the induced derivation on these finite dimensional vector spaces are just endomorphisms. And then you consider the classical Jordan decomposition for, let's say, finite dimensional vector space. And then you see that these decompositions, they are compatible with projections. Okay? So this is the way to, so the definition is that ds, let's say, dk decomposes dssk plus d nilpotent k for OK. Yes, sorry, yes, there's both are derivations, of course, and you can prove that. In fact, this decomposition is very, very robust in the sense that if delta is a derivation, you can prove that these both are derivations, and this holds. There is an argument to prove this. But I would like just to stress that the nilpotent property here is a property that holds in the finite dimensional vector space. And of course, in the, let's say, for this infinite dimensional context here, the nilpotency means that when you iterate this derivation sufficient number of times, then the order increases without limit, right? So this is semi-simple. And this is nilpotent. Okay, so just to make some small examples. So let's say suppose you start with a derivation which have this form here. Okay. And now we put some high order terms here. And then, of course, you know all know this. Is you take this set of eigenvalues lambda I, and then you say there is no resonances. And in this case, you can show that you can formally diagonalize this derivation. And so in this case, delta is delta SS. Okay. So a very important thing here that is going to be, let's say, the heart of my talk is that these two derivations here live in principle in this space, right? Because they are obtained by the projective limit property, right? So a second example, so just to show some things where the same simple part is not immediate. Take this case. So this is a one saddle. So eventually in this case you can have a non-zero nilpotent part, which is something like this. Can be something like this. Okay, so x dx plus y dy. Okay, so in this case you can. Sorry, I forgot to put an important condition here. So, of course, which makes this decomposition unique is these two properties joined with the property that this derivation should commute. Okay, so the Lie bracket of them is 0. Okay, so if you look at these two. Let's say these two terms which appear here, you see that this is already semi-simple. And the second one, it commutes, it's nilpotent because there's this order n here. And so they commute and satisfy these two properties. So this is the semi-simple nilpotent decomposition. Okay? So just very quick, some properties. So as I said, that's it's a very robust decomposition in the sense that all objects which are invariant by delta are also invariant by semi-simple part and nilpotent part, and reciprocally. So for instance, let's say all invariant objects of delta are delta SS and delta nilp invariant. For instance, if you have a symplectic vector field, let's say, which preserves the area, let's say the volume, then delta S and delta nilp will preserve the volume. Another example, if you have an ideal in O theta, which is delta invariant, by this I mean that you have the derivation which maps the ideal into itself, it's equivalent to say that it's a delta SS, the I is contained, and so this is just linear algebra effect, okay? Because it's just the fact that in a finite dimensional vector space, if you have a Jordan decomposition, a subspace is invariant by an endomorphism, if and only if it's invariant by this semi-simple and nilpotent part. So, okay, the set of property is very important. Is that it's very functorial property decomposition. In the following sense, suppose that you have this ideal which is invariant. Okay, then you can consider, let's say, the quotient algebra like this, and then, of course, you have an induced derivation on this quotient algebra here, and it inherits a semi-simple and nilpotent decomposition, which in fact is the same thing as taking delta SA plus delta nilp. Okay, so the semi-simple part of the restrictions is this restriction of the semi-simple part, and also for the nilpotent part. Okay, so let's start. Yeah. So another property which is very, let's say, more analytic flavor is the fact that this decomposition, even if we start with an analytic derivation, it's not true that delta SS and delta NIP are analytic. Okay. Not analytic in general. Okay, so I just given a small example of this. I think it's perhaps the simplest example that you can imagine. So it's already in dimension 1. Okay, but in dimension 1, you have to take not the vector fields, but the automorphisms, okay, for diff C0. So here you have an analog of the Jordan decomposition, which is what they call the Jordan-Chevalier decomposition. Okay, so you take a diffeomorphism, another diffeomorphism here, and there is a unique decomposition as a composition of two diffeomorphisms, where this is semi-simple. Essentially, it's linearizable in a, let's say, formally linearizable. And then phi u is unipotent here. It means that essentially that is it's tangent to identity. Okay, and this is formally linearizable. And then, of course, the conditions that they should commute. Okay, so there is always a such decomposition, and it's unique again. And so let me give an example. So I've learned this example in a very good book. I forgot the name of the author, but it starts with L, and then something like this. Very nice book of. So what the example is the following: you take phi equals to exponential 2e pi p over q, z plus higher order terms. Okay, and so in this case you have the same simple part is just let's say also you capture this linear part here. And then there is a unit point part. Okay, so it's tangent to the identity. And okay, so I said that this semi-simple part is linearizable, but at the same time it's of this type. So the only type of derivation, or let's say automorphism of this type, which is linearizable, are those which are of finite order. So let's suppose by that this decomposition is analytic, so let's suppose by contradiction, okay? So, well, of course, it's first to suppose that one of them is analytic, and then phi SS is formally linearizable. As I said, since it's a finite, it means that it has a finite order. It's also analytically linearizable. Okay, so you can write phi SS of Z as its linear part. Okay, and then the commuting relation, which I wrote there, just by writing the Taylor decomposition, implies that phi in this coordinate here, so there is an analytic coordinate where you can put all this, the unipotent part should be of this form. Okay, and this is too much, in fact. If you look to tangent to the identity diffeomorphisms which have this form, this puts a very strong restriction on the Écale-Voronin moduli. So this is just a drawing that was in the, no, it's not appearing here, but the drawing that is in the affiche, no, the poster of the conference, just the object that is above the Franck's head. So I think it's one of his favorite objects is this Écale-Voronin classification. So this is So this puts two strong restrictions on Ekal-Voronin invariants, which, let's say, generically are not satisfied. Okay? So there is another examples, which are due to Elizarov. So he has a whole paper with several explicit examples for, let's say, PQ saddles, resonant cells in C20. Okay? So this is also a sort of examples of, let's say, in this case, for vector fields where this decomposition is not analytic. Okay? So, of course, in this case, the question is, we could ask, is when this decomposition is analytic, okay? Because, of course, this helps a lot already to, let's say, to try to understand the local behavior of the foliation. So this is one of the questions that Bruno asks. So, okay, so I would like to recall a very classic result of Dulac, okay, which says the following thing. So there is say the following. So let's go back to the case of a saddle, 1-1 saddle. I think his enunciate is for more general cases, but I will state in this case. So this is what we call the linear part of the vector field. Okay, S. Yeah, so there is some perturbation here. And now suppose that you have a Jordan composition such that there exists a formal series, F tilde, such that delta SS is S, and the nilpotent part is written as a multiple of the semi-simple part, formal multiple. Okay? So in this case, what Dulac says is that this decomposition is analytic. So there exists, let's say, analytic coordinates x and y, such that, and let's say an analytic germ f of f, not the same, of course. So in principle, you have to change a little bit, such that you have a convergent decomposition, Jordan decomposition. Fs, okay? So why this is interesting? Because, okay, so in this case, you can write your vector field essentially in this form, right? So it's let's say a multiple, let's put a direct S here. So it's just a multiple of this linear part. And of course, in this case, it's very easy to understand the foliation because it's just, let's say, a reparameterization of the linear foliation. So it's equivalent in the sense that Laura explained. So this is orbitally equivalent to the linear foliation. And this is what we call the integrable situation, right? Totally integrable situation. So of course, there is later on, there are several proofs of this result. In particular, there is a generalization by Maté-Mossu, where you have some, let's say, statement like if you have a formula integral, then you have an analytic first integral. And then there is also a version of Bruno for this, what he calls condition A. And there is a further generalization by Stolovich, where he considers, instead of considering one derivation, he considers foliations like this. Okay? Yeah, so now I think I can start to talk about this mysterious Bruno theorem. Okay. So I think it's a very nice idea. is to change a little bit this question here. So instead of asking when this thing is analytic, he asks where it's analytic. Okay? You're going to see I explain this. So his enunciate is a little bit hard to understand because it's not explained in, let's say, in intrinsic way. So in order to put in the simpler terms, I will suppose something here. I will suppose that we are in the logarithmic situation because it's easier to enunciate in this case. So by this I mean the following. I suppose that there is I'm going to fix, let's say, some system of coordinates, and more precisely, I'm going to fix a divisor given by the union of the hyperplanes. Okay, so all my derivations will preserve this divisor here. Okay, so just to be short, I'm going to talk about this. So, of course, what this means is that the delta, since each irreducible component which will also be invariant, it means that delta xi is contained in xi. And we also say this by saying that delta has an expression like this, fi xi d over d xi. Okay, so you can factor out the component xi. So I'm going to do this because it's easier to enunciate the result in this case. So as I said, if you have this kind of hypothesis, this is inherited by the semi-simple and nilpotent components. They are also logarithmic derivations. Okay? And now I'm going to define what we call the Bruno ideal. Okay, he doesn't call it like that, but. So what we do is, let's say, we try to mimic this, let's say, the enunciate of the Dulac's theorem. So I'm going to define the following thing. Okay, so you can see that D is a free model, okay? Over E or E tilde, depending on the situation. And then we can take the, let's say, the exterior product of D over D. And here you can look at this element here as an element in this exterior product. And what I'm going to look at is the ideal, the vanishing ideal of this. Okay, so you can write this in a basis, and you look at the coefficients, and you look at the ideal where, so geometrically, this is the ideal where the semi-simple part is collinear with the nilpotent part. Okay, so like this. But of course, this cannot, perhaps this doesn't happen everywhere, but it happens inside some ideal, which is formally, okay? It's a formal, of course, because it's a formal ideal, and we cannot talk for the moment about variety because it's just a formula, perhaps a formal variety or something like this. Okay, so this is the Bruno ideal. So it's the collinearity ideal between the semi-simple and nilpotent parts. Okay, okay. So let me just give a more explicit expression for this ideal here, because it's nice. So one thing that we're going to see, that's the B of delta is delta invariant. And in particular, is also delta semi-simple, delta nilpotent invariant. Okay, so how to, there is a formal presentation of this. Which is easier to compute, is the following one. So you take, let's say you have the semi-simple part, and you can linearize the semi-simple part, writing it, diagonalize S. Yes. So there are formal coordinates, x1, xn, which also respect of course, they are not the original coordinates, but they respect the divisor, such that you can write delta S in this form. So this is my notation for the diagonal derivation, which eigenvalue is lambda y. Okay? So in this expression here, if you impose, so let's complete lambda delta to a basis of the logarithmic derivation. So this is a commuting basis, so this vector field is a commute. And they are all of this type, okay? So basis of D. And in this base, I can expand also the nilpotent part. So it has to be something of this form. F L lambda plus G E L mu E. Okay? And now, if you compute in this basis here, the ideal. So, okay, of course, so the basis of this vector spaces here is just obtained from exterior product of these elements here. And then it's easy to see that the collinearity ideal is just the ideal generated by G1, Gn minus 1. Okay? So I forgot to say the property of commuting. When you impose the property that delta SS, delta nit commute, this corresponds in this simple case to say that the F and the GI are resonant functions with respect to L lambda. So it means the following thing. So you can decompose, since you have a semi-simple object here, you can graduate this space in terms of weights. Okay, so these weights will appear later on. So, L, so this delta SS. So this is the graduated component. So a component here is just a germ, eventually formal, such that delta S of F is equal to alpha F. Okay, so this is a homogeneous components of weight alpha. Of course, alpha can be a complex number. Okay, so the resonance condition here implies that the coefficients F and Ji are what we call a resonant terms. They live here. Okay, they are graduated zero components. So this is the ideal, right? So, of course, this ideal, as I said, is a formal ideal. So we have to see this as an ideal lying here. Okay. So now I think I can. So sorry, I forgot to say, but using this decomposition, say this formal representation, it's quite easy to see that this Bruno ideal is invariant by the derivation. As I said, this also implies that it's delta SS and delta nilp invariant. Okay. So, of course, I think you can imagine what Bruno says. It says that inside this ideal, you have somehow a convergence, right? So the convergence happens inside the Bruno ideal, and using some arithmetic conditions on lambda, you can prove that this ideal is analytic. Okay. Well, I'm just going to give a small example because it's very motivating. It's what they call a variety of centers. Okay. Let's say like this. So let's take delta as a one-parameter family, where the linear part, it's just a pure rotation. Okay, so real vector field, let's say. And then I have some epsilon perturbation here, okay? Right, so in this case, this is I'm going to see this as an epsilon family, but it's a family of two-dimensional vector fields, okay? So this component is not very dimensional. So, okay, so how is the normal form here? What's the general decomposition here? You just have things like this. This is 1 plus f the x squared plus y squared epsilon times this first term here. And then there is a second term, which is written in terms of the resonant monomers, which in our case are these ones, times something which is orthogonal, let's say complementary to this. Sorry. I can take this element of the basis, the radial vector field. Okay. But I could take another one, just to have a basis. Okay. So, of course, in this case, the Bruno ideal, as I said to you, is the ideal generated by this. Okay. And, of course, if you can, so it is an ideal which lives in the set of formal series written in these two monomials. And now let's make a small drawing here. Let's say, hope let's motivate something. So you have this initial point here. And when you look at this Bruno ideals, let's suppose that it's convergent. So this is the epsilon coordinate. You are looking to, let's say, I'm going to plot here the zero set of G. So what you're going to see that this zero set will be filled in with periodic orbits, right? And of course, this is due to the normal form. So what we are going to capture here is all the periodic behavior which happens nearby the singularity. So the sort of center variety of periodic orbits or a variety of centers. Okay. Of course, this is this kind of result in dimension 2 could be proven in much easier way, to prove that this red object here is analytic, could be done in very much more easier way because, of course, if you look at this linear part here, you see that it's, of course, it's hyperbolic singularity, so it's preserved by perturbations. So you can rectify, let's say, by imposing that this corresponds to the epsilon axis, and then you make a blow up along the variety hyperbolic. And what you're going to see is that there's something like this, right? And then if you take a transverse section, you have the Poincare map. And of course, you capture this red object here. It's just the set of periodic orbits, so it's captured just as the curve of fixed points of the Poincare map. So of course, there's a much more geometric way to prove that this variety is analytic. But the Bruno's result also holds in more, let's say, complicated cases. Perhaps I'm not going to write. But suppose that you have, let's say, a space of dimension of even dimension, and then you have the linear part is divided by a sum of rotations of different frequencies, right? So essentially, what you have is that in this space you have, let's say, the linear part gives you the solution curves are tori, which are filled in with periodic, let's say, with quasi-periodic movement. And you can imagine that there is some sort of variety where this tori persists formally. Okay, so the idea is that if you have this tori which persists formally, our goal is to prove that there is a real analytic variety which is filled in with tori which have the same, let's say, leaf behavior. So I think it's time to enunciate the theorem. Yeah. So I'm sorry, because I have to state the Bruno's condition. It's part of the result of the enunciate, sorry. So there's this famous, I think most of you know this Bruno arithmetic condition, but I'm going to state quickly. So this is the conditions which will guarantee that this Bruno ideal is an analytic ideal. Okay? So let's say, to be precise, I say that an ideal, a formal ideal, is analytic. So the definition, let's call it G. If, so there exists an ideal, analytic ideal such that, so this G is just the extension of this analytic ideal to the completion, right? So essentially it means that you can find analytic generators for the ideal, which is in principle just form. So I'm going to use this enunciate in my statement. Okay, so what is the Bruno idea? The Bruno condition is a condition about the weights of a representation of a semi-simple derivation in the local ring. Okay? So as I said to you, you consider a semi-simple derivation, any one, and now you can decompose O tilde as a sum of graduated components, as I explained to you before. Sorry. So this is a O tilde S. But at the same time, you can consider the decomposition of the jets, right? So the jets also decompose as a direct sum like this, because the jet spaces are invariant. Okay. And so I define the weight of GK with respect to S. Let's say as this is a Lie algebra type of naming this is just the weights alpha, such that the graduated component, the alpha graduated component, is different from the trivial subspace. Okay, so this is the weight GK, and now I define the non-zero weights as being, well, of course, this is the weights times minus 0. Okay, some sense in this case, I'm just removing the weights, the subspace corresponding to the resonant monomials. So what's the Bruno's condition is that he takes omega k as being the minimum for each k of the, let's say, the module of alpha belonging to weight star G. So this is 2k here. Okay, so this is due to the Newton's algorithm of convergence. Okay, so just take the weights, the non-zero weights in this 2k jet, and then you ask this series to be, this is the omega condition, you ask this series here to be convergent. Okay, so this is the omega condition. It's log, sorry. So it's a very weak condition on the weights. Of course, this can be also rephrased in terms of the eigenvalues of the linear part. Yeah. So now the theorem of Bruno. This is the mysterious theorem of Bruno, as I said. So suppose you start with let's say, analytic derivation. Analytic, okay. Logarithmic, as I said. So such a derivation, okay, such that its semi-simple part, which is intrinsically defined, of course, satisfies the condition omega. Okay, so this is a condition which is intrinsically defined with respect to the weight decomposition associated to the graduation of the space, right? Then two things. First thing, this ideal is analytic. Okay, so this somehow answers the question that I put there, where the decomposition converges, because the second part is that if you now you have, since it's analytic, you have the right to write the variety, let's say the germ of analytic variety associated to this ideal, and both vector fields, let's say all the three vector fields leave this variety invariant, as I said. So in restriction to this variety, let's imagine something like this, right? Singular variety like this. So in restriction to V of delta, you have, in fact, let me just note like this. So the restriction of the initial derivation to the Bruno variety is a multiple of its semi-simple part. And most especially, you can write this in this form, where so you can not only, let's say, write the vector field as a multiple of its semi-simple part, but you can also linearize so this linearization or diagonalization of delta SS. Okay. Yeah.
Do you have a change of coordinates in the ambient space?
Yes, that's the idea is that it's very, let's say, this is why it's quite counterintuitive for me at the beginning, because you have this change of coordinates that you do in the ambient space, and the idea is that you only, of course, you don't want to have a formal, let's say, you have to keep to the convergent world, but so in this case, what you want to control is not what happens in the ambient space with your decomposition, but at each time you restrict yourself to somehow the jet space restriction of this B of delta. Okay. Okay. So I have perhaps for memes. I just explain to you very roughly the idea of this proof. So for this, you have to understand the classic linearization. Okay, so due to Bruno, because his main contribution, I think, was to prove really that under these very weak conditions, you have the convergence. And in fact, the idea is that you have a sort of a formal convergence to this kind of decomposition. And you have to control, of course, the coefficients that you are going to impose each time that you make an improvement, right? So the idea that you have an iterative algorithm, Newton type algorithm. This is not new, okay? So let's say I'm going to suppose, just to simplify, that we start with the linear part like this, right? And then at the k step, you have a rest term, which is something like this. So it's all the coefficients of this rest term here are just elements which are going to note like this. So there are elements which have a valuation greater than 8 to m to the power 2k. And then there is a chain of coordinates, which also will be something like identity plus m to the power 2k, right? So very flat to the identity, where I'm going to improve this part, right? And then get something of the type m2 k plus 1, so I double the precision at each time, like this, right? But, of course, this is always possible when there is no resonance. I mean, you don't leave any residue here, in the sense that you can completely eliminate the polynomial part which lies between this order and this order here. So essentially, you have to solve polynomial equations at each time, and the solution. So let's say the chain of coordinates which appear here is given by an exponential of some vector field, where this is the essential equation to solve, right? So it's called the co-cycle equation. Okay. You have this rest term, and then you have to find an U such that this holds, right? So, and as I said to you, if you write up the equations, this is a sort of partial differential equation, but in polynomial coefficients, because you are truncating things here, right? And then the idea is you under this Bruno's condition, you control the inverse, right? You have to control the size of these coefficients of u in terms of the coefficients of this. Okay, so you control this inverse map here. Okay, but so I'm going to finish this. What happens is that if you have some resonances, as I mentioned here, this is precisely the case where you have this f which will appear here. Okay. Then things get much more complicated, because you see at the k step, you have something like this. You have a resonant term plus the thing that you want to eliminate. Okay? And this resonance term is formally, let's say, it's a formal invariant in the sense that you cannot get rid of it by this kind of operation. And so you have to keep it in all the sequence steps, right? So when you try to solve this equation here, what you get in the place of this simple, very simple diagonalizable equation is something like this kind of object, right? Where now you have to solve this thing, right? And of course, the problem is that there is a huge difference, and this is why this condition holds. There is a huge difference between the way to bound the norm of the inverse map depending on the type of terms that you obtain here. So if this term is of type f of L lambda, as I said here, let's say you have something which is multiple of the semi-simple part, then you can still bound. But if you have something which is not a multiple of then this is unbounded. There is counterexamples to show that this is in this case, you cannot have convergence. Okay, so I'm going to stop here. Thank you very much.